All right, good morning, everybody. So going back to the last problem for just a moment, looking at this from a big picture standpoint, first, to find the derivative at a particular x value at a particular point, we start with our limit definition of the derivative. So what's the limit? As the distance between the 2 points, or the h value, the hair beyond tangent point, approaches 0. Then we use the formula for the slope, f of x plus h, the y value of the hair beyond point, minus f of x, the y value of the tangent point, and then x plus h minus x. So that's what we are going to start with on all of these derivative problems. And then after that, it's really just plugging in, simplifying, and then our large goal is to get that divided by h in the denominator to cancel, so we can use direct substitution to find the limit. So after we have plugged everything in, our goal from the very beginning is to get rid of that h in the denominator, because until we get rid of this h, until we are able to factor and cancel it out with something on the top, I'm not going to be able to evaluate this limit because I'm not going to be able to plug in the 0 for that h. So when we start simplifying, and the more of these we do, we're going to start seeing some patterns. For one, when you get to all your foiling, distributing your negatives, all of your just plain numeric stuff like the 9s in this problem and the 1s, or in the future when we start doing generalized formulas, all of your x stuff will cancel, and you'll always be left with terms that only have h in them. That's always going to allow you to factor out an h to cancel out with that h in the denominator. So that's our large goal in these problems, and it's also a pattern that we will start seeing as we continue to work through these. So take a deep breath, and looking at the next problem, we've got a new function that we are looking at. Now, this function is again a quadratic, and I've went ahead and put this in on my calculator. So there's what my quadratic looks like, and what we want to find is f prime of negative 3. So what we are looking for is the derivative at negative 3, or the slope of the tangent line at x equals negative 3. So on my graph, if I do trace negative 3, we see that the tangent point I'm looking at is negative 315. So if I imagine drawing a line through that tangent point, so just touching our graph in that one spot and going down, what do we know about the slope of this line just by looking at our graph? Since it is going down and to the right, we can tell that the slope is going to be negative, and it's also going to be fairly steep. So again, just like we did this to kind of check ourselves on the previous problem, it's not a bad idea to check yourself on your calculator to see if your final slope value does make sense with your graph. So we are now ready to start with our limit definition of the derivative. So what are we looking for? F prime of negative 3, or the derivative at negative 3, or the slope of the tangent at negative 3. And this is equal to the limit as what approaches 0? As that h value approaches 0. So that's saying that we're closing in on our 2 points, the tangent point and the hair beyond point. If we close in on that distance, or as that distance approaches 0, we're going to get super duper close to, instead of finding the slope at 2 points, to finding the slope at just 1 point. So sometimes on tests, students will accidentally put as x approaches 0, just because that's typically what we've seen in all of the other limits that we are looking at. But here it is the h value, because that's the distance we want to approach 0. So then we write our slope formula starting with the hair beyond point's y value. So f of x plus h minus f of x. And again, we want this one to come first, otherwise you'll end up with a negative h on the bottom. So the x plus h point comes first, the tangent point comes second, and then all over x plus h minus x. Now, folks, you don't have to show this part on the bottom. You can just go straight to having just h, but I like to sometimes write this because it's a reminder that, hey, this is really just the slope formula. Here's the y value of those points. Here are the two x values, and it's because those x's cancel that we are left with just h on the bottom. And again, folks, this is the limit definition of the derivative and what you will want to have memorized. Very, very, very important for calculus. So from here, it's just a matter of simplifying and trying to get that h on the bottom to cancel by factoring and canceling to do direct substitution. So we're going to go ahead and start with the first part of this expression. And remember that limit as h approaches 0 is going to be carried through this entire horizontal line. So let's start with f of x plus h. Well, our x value here is negative 3. And then we've got minus, and then f of negative 3. So we're just plugging that x value in for those x's. This is all over h. Next, we are going to plug these values into our actual function. So this is f of negative 3 plus h. So if I wanted to find f of 2, you'd plug in 2 for this x. Because we want to find f of negative 3 plus h, that's what we're going to plug in for that x. So, being careful with our parentheses, we will have 2 times negative 3 plus h squared minus 3. So that's what happens when we plug in negative 3 plus h into our function. And remember, folks, sometimes I use this minus sign as sort of an anchor to tell where I'm at in the work, because some of the ones we do will get kind of lengthy. So then we have our minus sign. And then f of negative 3, we're going to plug negative 3 into our function. And remember, folks, we're going to need to enclose this whole thing in parentheses because I'm subtracting that entire f of negative 3. So we're subtracting this entire expression. So 2 times negative 3 squared minus 3. All right. And that's what happens when we plug negative 3 into our function. So you can see why there's a lot of negative 3's going on here, and this is why I kind of like to underline and box that negative just to kind of keep my work a bit more organized so I can tell what it is I am doing. Also, don't forget, after we do all that plugging in, this is still all over h. So before we move to the next step of simplifying, folks, I would like you to write PEMDAS. Good old PEMDAS, Algebra 1, coming back to haunt us. Because anytime we have a quadratic, anytime we are squaring, especially negative numbers and binomials, we do need to be careful to make sure we do it correctly. But again, folks, what's kind of nice about this is, as we start doing more problems, what you'll find is that if you aren't able to take out an h from everybody in your simplified top of the fraction, it means you done goofed somewhere. So let's go ahead and drop down to our next line. And remember, when you drop down to the next line, you got to rewrite that limit notation. So the limit as h approaches 0. So from a PEMDAS standpoint, in this light green expression, we're going to start first by handling the exponent. Sometimes students will try to distribute that 2 in first, but since exponents come before multiplying in PEMDAS, you have to do this part of the expression first. So that's the first issue with this problem. The other issue is remembering that we have to FOIL. So we're going to have 2 times negative 3 plus h times negative 3 plus h. And I'm going to go ahead and just write that above. It just helps me to visualize it. And when I FOIL that, we get a positive 9, a negative 6h, and then a positive h squared. Then we've still got that scuzzy little -3 hanging out. So this is still that original light green expression. Then I've got that minus sign anchor. And now we are going to do PEMDAS on the dark green expression. So again, we have to do the exponent before we do our multiplying. And folks, I've already gotten a couple of questions on the My Math Lab. Please, please, please make sure that if you are using your calculator here, you do include those parentheses, because -3 in parentheses squared is +9, but the opposite of 3 squared without parentheses would be a -9. So those parentheses are important, but folks, with the small enough numbers, I would just go ahead and evaluate this in your head. -3 squared is +9, times 2 is 18, and -3 is 15. So we get minus 15. And this is all over h. So my next step in simplifying is distributing that 2, which gives us 18 minus 12h plus 2h squared, then the -3, and then the minus 15, all over h. And now we are ready to combine our like terms. We've got 18 minus 3, which is 15, and then minus 15 is 0. So goodbye to these terms. And what we are left with is just like what we expected, an expression on the top, all in terms of h's and h squareds. So once I get to this point, before we can do direct substitution, I can't plug in 0 for h currently, because that would be dividing by 0. That is undefined, and that would be a whole at that value. So what we need to do instead is factor and cancel. So we're going to factor out an h, which leaves me with -12 plus 2h. And you could have the order of those flipped around. You could have 2h minus 12. And then, ta-da! We can cancel out those h's. And once that h in the denominator is gone, that's when we get to do direct substitution. So now we are ready to actually evaluate that limit and plug in that 0 for the remaining h in the expression. So that leaves me with, and notice that I'm changing just my running equal sign to the equal sign with the arrow to show that that limit that we've kind of been carrying through horizontally this whole time, the limit, once we do direct substitution, goes away. Once I plug in that 0, I am no longer evaluating that limit. Oh, I no longer have that limit notation out in front because I'm evaluating the limit. So this turns into -12 plus 2 times that h value of 0. And so we just get -12. What equals -12? Why, that original part of our expression, f prime of -3. So all that crazy work, and we just get a nice little straight up number value of -12. So what does this mean? First, the derivative is the slope of the tangent. And no, folks, you don't have to do this on your homework. We're just going to keep doing this in our note packet, though, to really emphasize what this new concept is. The slope of the tangent line at x equals -3 is -12. So the -3, the slope of the tangent is -12. And is that reasonable with what we found by looking at our calculator? If we go back to our calculator, does it seem reasonable that -12 would be the slope of a line running tangent right at that point? yeah, negative 12 seems pretty reasonable. And we're going to take this a step further because this will help you on the My Math Lab assignment that's all about point slope form and finding the equations of lines. We are going to find the full-on slope intercept form equation of this line. So currently, we've got the slope and we have the tangent point. The slope of the tangent is negative 12 and the tangent point is negative 315. So that's going to be our x1, y1 in point slope form. So y minus y1, y minus 15 equals m, negative 12, times x minus our x1. Ooh, a double negative, so watch out for that. So then we get y minus 15 equals negative 12x. That's plus 3 times negative 12 is negative 36. And then add 15 to both sides. And we get y equals negative 12x minus 21. So this would be the equation of the tangent line. The equation of the tangent line. And what's nice is once we have the equation, we can actually type that in on our calculator. So let's see, negative 12x minus 21. And we can see that it is touching right at that point. And if you really wanted to verify that, to find the intersection point, you do second trace, intersect, enter, enter, enter. And there's our tangent point, negative 315. So this is just kind of a nice visual of what did we actually find? We found the slope at that particular point for the tangent line. Now, what we're going to start exploring on the next page, or actually it's probably 2 pages from now, is as we start looking at different points on different curves, the slope of the tangent is going to change. The slope of the tangent line on this side of our graph is going to be negative, but the slope of a tangent on this side of this line would have a positive slope. So that's what's kind of interesting, is the slope of the tangent is going to change as we move on our graph. Nice work.